to introduce Professor Dong Lai for our inaugural 2024 CITA seminar series. Dong is the Benson J. Simon and Mary Ellen Simon Professor of Astronomy and Astrophysics at Cornell University. He's been faculty there since '97 after a three-year stint as a postdoc at Caltech prior to that. He's an expert in astrophysical dynamics, both the fluid sort and point particle sort. He has research interests ranging from compact objects to exoplanets, all across astrophysics. So without further ado, I'll let you take it away.
Thank you, Sam. Hello, hi.
You made it.
Good, thank you. Should I do the?
Oh, you don't have to. The owl thing here will pick it up. So if
How
you
do I
wanna,
change? I just change.
do you want to? You can turn your camera off on your laptop if you want, or I'll just make that
Okay.
tiny.
All right, good.
So that's out of the way.
So I just okay, good. It's always a pleasure to come to CITA. It's one of my favorite place, Toronto. A lot of friends here, and okay. So I want to talk about formation of merging black hole binaries. Okay. So let me first very quickly go through some slides I think most people are familiar with. So it's not moving.
Nothing, right? So something up here.
Turn up volume.
Turn it up. Let's see.
Like this?
Yes,
Oh, okay, good. Now it's good. Thank
Left and
you.
right.
Your magic hand. Okay, now it's good. All right, so I think we're in the new era of gravitational wave astronomy. We have 90 events already. LIGO 03, 04 is ongoing, and they are mostly black hole mergers, and there are 2 neutron-star mergers so far. Some black hole neutron-star mergers. And these are gravitational wave basics, warpage of space-time, LIGO, how LIGO detected, and these are the, get rid of this. All right, so these are the 90 events, right? So these are the observables. If you look at, for each LIGO event, you can measure the masses of two black holes, and the constraint or measure the chi-effective, right? This chi-effective, it's the chi1, chi2 are the current parameter for each individual black hole, the vector, right? So this is mass-weighted spin projected along the orbital angular momentum axis. So this is a quantity that can also be constrained or measured. Okay, so these are the 3 quantities that we have from gravitational waves. Okay, it's frozen again. What's happened?
Actually, I have better success with left and right instead of up and down. No?
What happened? What did you do?
I clicked on the little arrows on the bottom.
Okay. Yeah, I think it has an inertia if I stop. Yes, okay. All right, so what can we do with these gravitational waves, right? So let me just go through some quickly, right? Of course, the first thing you can do is test gravity, right? And linear regime, and many people are engaged in these activities, right? And so far, I was talking with my colleagues, Cornell and Caltech, and GR works perfectly, right, so far. Right? And the second thing you can do, of course, is study dense nuclear matter. When you have 2 neutrons that collide with each other, there are a lot of dense nuclear matter physics involved. And before the merger, you have tidal effect that can affect the waveform. And after the merger, you may have interesting things affecting the merger signal, right? And you can also study nuclear synthesis, right? Because they produce R-process element that can power the electromagnetic radiation that have been observed in this famous event. And finally, you can do astrophysics, by which I mean you can try to understand where these merging black holes come from, right? Where are these black hole binaries come from? So that's what I want to focus on in this talk. Okay? First, we have this obvious merging time scale, right? We have two binary components, M1, M2, but in this case, total mass, 60 solar mass, reduced mass, 15 solar mass, right? This is the merger time, right? So we have this so-called final AU problem, right? In order to have these two black hole merge within Hubble time, the separation must be less than about AU also, right? So you want to bring these two black holes usually far away from each other, close enough so that gravitational radiation will take over, make them merge, right? So that's the final AU problem. And of course, many people have been engaged in this, in trying to understand how can you solve this final AU problem? How can you bring these two black holes close enough so that gravitational radiation can take over? So that's the goal of many of these activities, right? So there are, roughly speaking, two general formation channels, right? The isolated binary evolution, and then several different flavors of dynamical formation channels, which I'm going to talk about, involving star clusters, triples, multiples, and finally AGN disks, right? But before I talk about them in some detail, we should first think about how we are going to distinguish different channels, right? What are the observables that we can use to potentially, in the future at least, distinguish different channels, right? First, of course, rates that are certainly very important. Usually, in many of these situations, it's highly uncertain. You can imagine, right, involving a lot of different steps. So the rates are usually very uncertain. Right? I'm not going to talk about the rates in this talk. The mass ratios are another very important observables. Residual eccentricity is very important because, of course, as you know, that when you have an eccentric binary, the gravitational radiation makes the orbit decay. The eccentricity also goes down, right? Gravitational radiation also circulates the orbit. So, but if you have something that you formed very, very eccentric, close to merger, then of course, when you enter the LIGO band, they can still have some residual eccentricity. That would be very important, right? And then finally, we have the spin orbit misalignment, like the angle between the spin of the individual black hole and the orbital angular axis. And this is important because, as I just told you, this chi-effective depends on the angle between the spin of each black hole with respect to the orbital angular axis. So that angle is important, right? Right. So spin orbit angle is important. And finally, of course, in some scenario, you might expect you may have electromagnetic radiation, electromagnetic counterpart. That's also potentially important. Okay. So these are the potential ways that you can distinguish different channels. So now let me go through some of these formation channels. Right. The first, of course, the well-known, the standard, perhaps most conservative one, basically, the isolated binary evolution standard for channel, right? And there have been many papers over the last few decades studying this problem, right? It's most likely will happen, but there's some uncertain physics, right? The physics uncertainty involves the common envelope phase. Basically, if you look at here, there are stages during the evolution starting with two main sequences of binary. During the evolution, there are stages where you have the star expand, engulfing the companion. You have this common envelope phase, which is exactly how the thing evolved during whether these two components can merge, can shrink in orbit, but not completely merge during this common envelope phase. It's an open question, it's a difficult problem, right? And it may work, but it's not clear. There's some uncertainty in that physics, right? And regardless of this uncertainty, we are reasonably confident that you produce more or less circular orbit simply because you have this, everything inside the common envelope, right? Everything circular, and you most likely produce a aligned spin orbit, right? In this kind of scenario, right? And there's a variation of this isolated binary evolution channel called chemically homogeneous evolution, where you imagine the two main sequence stars are already very close to each other at the beginning, rotating very fast by tides. And because of a rapid rotation, the star is dynamically, a lot of instability is going on. So instability gives rise to mixing, turbulence, and the whole thing constantly mixed up. as a result, the stars never evolve off the main sequence, stay on the main sequence all the time, and then they evolve eventually become two black holes, right, and merge. Right, so these are the two flavors of the isolated binary evolution. Now the dynamical channel is something I want to focus on. A pointer I can use, maybe I try to understand, but it's hard to find. It's fine. I can. Okay. So there are several different flavors of dynamical channel. The first one that most familiar with people you are familiar with are these involving dense star clusters, right? And the key physical process it's all involved this. It's basically binary single scattering, right? So you imagine in dense stellar clusters, you have binaries, certainly, you have singles, they're moving around, and they can have close encounters. Binary being big, they have relatively large cross-section of these close encounters. When you have this kind of binary single scattering problem, it's complicated, but one possible outcome is that after this thing intact, one of the three bodies will be ejected, leaving behind, taking away some energy, leaving behind a binary that's more tightly bound than before. So that's how you shrink the object, basically, right? And so the physics is very clean in this problem, very clean, right? The uncertainty mainly in the astronomy, basically the environmental uncertainty. For this, basically, we have enough black holes in the cluster. What kind of cluster we're dealing with? Globular cluster or cluster around supermassive black hole, right? And what happens there? The black hole may not stay in the cluster because when they have collapse, right? And they may have a kick, may not stay in the cluster. So that's a kind of environmental astronomical uncertainties that we have to deal with, right? The physics is very clean, it certainly happens, right? And so many people have done a simulation, so it's most likely will produce circular orbit when the black hole binary enter the LIGO band, simply because the orbit is really, really big. So when you come in and eventually decay, it's circularized, and you expect random spin orbit orientations because you have this random scattering process. Okay, so that's a dense cluster channel.
Why is it circular again? Sorry, the scattering itself doesn't.
Yeah, so basically, it's does not have to be. It's just typically the orbit after the third one gone. They're still quite big. It takes time to when they merge.
Is it?
They exactly, yes. All right. So the second general classes of dynamical channel is what I call tertiary induced merger. Here it also involves three or four bodies, except it's more gentle. The dynamical process is more gentle. So instead of this kind of violent scattering process, you have the third body perturbatively change the orbit of the binary. You have a binary here, a third body, right, gradually changing the shape of the orbit and making the binary orbit shrink and decay. Right, and this tertiary, the third body, could be another black hole, another star in the galactic field, or could be a supermassive black hole. If you imagine you have a binary black hole orbiting around supermassive black hole in a star cluster, right? You have a supermassive black hole there, and they can. So this could happen, right? So this is something we have been spending some time in the last few years doing, and tertiary induced merger. Now, this is not new idea, and in fact, many people have done this kind of problems, studied this kind of effect, tertiary-induced merger, in different contexts, including merger of supermassive black hole, for example. Right? So I want to summarize what we have found, some of the new things we have found in the last few years, and in the next 15 minutes. Okay. Right, so before I talk about the details, let me just summarize some of the key implications of this tertiary induced merger, right? Typically, this kind of merger would use circular orbit that some fraction of the systems would have finite eccentricity, 0.1, 0.2, small fraction, okay? And you tend to produce broad spin orbit angles, with a slight peak around 90 degrees. I'll explain why. And in the galactic field, for example, if a binary, the third body is another star or another black hole, stellar black hole. In this case, everything else being equal, this kind of channel tend to prefer unequal mass merger. Okay, unequal mass merger, right? Now, this might be constrained by maybe constrained by LIGO data already. And if you are talking about binaries around a supermassive black hole, in that case, the tertiary, it's a supermassive black hole. In that case, there's some additional GR effect associated with the spin of the supermassive black hole that can enhance the merger, the probability of merger. So this black hole supermassive spin of supermassive black hole can actually affect the dynamics. So that's some of the implications. So okay.
Is that really important statistically, number 4?
We don't know yet. We don't know. Statistically, we don't know yet. We don't know anything.
I mean, you can get Kozai happening, at a very wide orbit, right?
Yeah, but not always. Like if you have a typical condition,
you can have a
you can have the same. You can. It's not so close, actually. Not so close. Not so close. Let me go to that part. Okay. Okay. So the key effect, of course, Kozai, lead off Kozai effect. I know many people have studied Kozai, familiar with this. But just maybe show a hand. Who somebody don't know Kozai? Maybe nobody. Okay, good. I can skip.
One dipole.
One dipole, yes. Okay. Anyway, let me just. I don't want to spend a lot of time. Just basically, what's happening basically is you have a binary, right? Normally circular orbit. They're far away from each other, from merging. From the far away, they cannot merge by themselves. But you have a third body, right? But could be far away, and then if the third body's orbit is highly inclined, 70 degrees, 90 degrees, 80 degrees, right? Then the third body, the perturbation of third body can make the orbit go into eccentric orbit, and and therefore once the eccentric orbit, very eccentric orbit, then the orbit can shrink, right? So here is the example. So here is the example, right? So here is the here is the example. You have in the binary, so M1 is 30 solar mass, 20 solar mass, right? Initially separation is 100 AU. So they cannot merge by themselves, right? But you have a third body, M3, 30 solar mass, very far away. The A out is 6,000 AU, right? So you can see the third body is very far away. Nevertheless, if you imagine the initial inclination, let's say it's 92 degrees, close to perpendicular, right? The two orbits are almost perpendicular. In that case, the third body can make the inner orbit eccentric and go to very eccentric, high eccentricity, 1 minus e 10 to the minus 4. So that means even though the orbit semi-major axis is very large, at pericenter they're very close, right? And when they're very close, you can have gravitational radiation and they can shrink the orbit, right? And so you can see this example, initially 100 AU, eventually merge, right? And the inner orbit goes through Kozai cycles of eccentricity oscillation. Okay, all right. So that's the thing. That's how it works, right? Now, this effect is mostly quadruple order effect. Basically, you have a third body, third quadruple potential on the inner orbit, right? And this is a quadruple effect. So the strength of the effect depends on the mass of the third body divided by the semi-major axis third body, the cube power, right? In the quadruple order, this problem is very analytic. You can actually solve everything analytically, right? You can write down the equation, you can solve, integrate them, right? And you can actually predict the merger window, basically, in order for the inner orbit to merge, the inclination of the outer orbit must be sufficiently large such that you can induce enough eccentricity. You can, like, this can be calculated analytically, right? The merger window, right? So in this example, for example, you have to, if you want to inner binary to merge within Hubble time, the cosine of the inclination angle must be within a narrow range around this 90 degrees. Okay, around 90 degrees. Cosine theta, cosine I inclination must be close to 0. Okay, and so it's it's a very narrow window basically, right? It's, it's a very narrow window, right? And this is analytic. Now, if you go to high order, of course, you can if you imagine adding perturbation, high order effect. Then the next order, of course, it's the octuple order effect. The strength of octuple relative to quadrupole depends on this dimensionless parameter, right? A of the inner orbit divided by A of the outer orbit. It also depends on eccentricity of the outer orbit. It depends on the mass differences between the two orbits, the inner orbit, right? So if you have sufficient octupole, that octupole can play an important role, can change the character of the lead-off cosine oscillation, making the evolution chaotic, okay? And you cannot solve it, you actually have to integrate this thing, right? And the main takeaway for the octupole effect is that even though it's chaotic, there's still some rule that you have to satisfy. In particular, you cannot get arbitrarily high eccentricity, even with octupole. There's a misconception in the community. They do a lot of things with octupole, but there is a maximum eccentricity you can get. You cannot arbitrarily increase it basically beyond that, simply because
So
this can be computed.
where, in your opinion, is the binary most likely to be? I saw the triple is most likely to be.
This I'm imagining the galactic field.
Okay.
I'm imagining galactic field.
So in other words, the outer orbit is going to be fairly stable. It's not going to be perturbed by a fourth body frequently.
Yeah, it's not going to be that galactic field. Okay, the main effect of octupole is that, to take away from this, is that basically the octupole can broaden the merger window. So I mentioned before, if you only have quadrupole, the window is very small. Basically, the outer orbit must be close to 90 degrees with respect to the inner orbit. But once you turn on the octupole effect, right, if it's sufficiently large, it turns out you don't have to be 85 degrees. You can still produce large eccentricity for a broad range of initial inclination. Okay, so this is a octupole broaden the lead-off current merger window. So, okay.
I'm sort of a bit confused by your horizontal axis. Isn't it at I equals 90 that you're always most unstable?
Sorry, I didn't explain. This is because it's not I equal 90 is basically if you imagine the inner orbit has negligible angular momentum compared to the outer one. So in this case, it's not exactly right. So So in this case, binary, orbital angular momentum is not negligible in the orbit. So it's not exact 90 degrees. It's actually
the best case.
The peak is slightly and this Okay, so main takeaway is that octupole can increase the merger window. Now, let's look at this expression for the octupole strength. So you can see, right, and the octupole depends on these things. So you can see, therefore, that everything being equal, if you have very asymmetric binary, namely if M1, M2 are very different, they tend to have a larger octupole, and octupole effect can be larger. So therefore, one would expect that, not surprisingly, right, everything being equal, so here, I put a system where total mass is 50 solar mass. By changing the mass ratio, you find the merger fraction increases when you go to asymmetric masses, binaries, simply because of it's rather dramatic, right? If you have equal mass, you only have 1%, and when you go higher, it's much higher. On equal mass, it becomes much higher.
And you're randomly
orientation, exactly. Random orientation. So this all can be understood, can be calculated. Okay, more or less semi-analytical. Okay.
But okay, I'm sorry to invite you, but is in fact it reasonable to assume random orientations given the actual formation mechanism?
We don't know, right? We don't really know, right? We don't know, right? If you look at the triple systems, that's the most statistic study. If you look at binary, if the third guy is relatively close, then they tend to be co-planar within 40 degrees.
Okay.
When they're far away, they tend to be random. So this is not a very, right? What is that critical separation? Typically, 400 degrees, 500 degrees. There's some study on this in the context of planetary system with in the binary system, planets, and then you have a third one. There's some study. Okay. Anyway, the point is I'm trying to illustrate here is just that this dramatic effect basically. Okay, so now is this compatible with the observed mass ratio distribution of the merging black hole binary? So here is the constraint current result based on O3 data, right? So here it's mass ratio distribution. So most of this is taking into account of the detection bias, right? You tend to detect equal mass kind of things, right? And here are the 90% error bar things, right? And okay, so you can see that nothing, no peak at the low Q, low mass ratio. So maybe this actually already ruled out this tertiary induced merger in the galaxy. It's already that for me that's fine. I think it's great that we right. Except I mean one has to be careful, right? Because it's possible that this what I told you about here is basically given the total mass, right? Given the thing, right? You have the preferred unequal mass. It could be that when you have a triple system, the inner binary nature can maybe give you something that most likely produce equal mass. It's still possible, right? So I'm not sure about that yet. Okay, so this just illustrates the possibility of confronting this kind of model with data. I think one can constrain the model. All right, so now let me move on to the tertiary, the tertiary induced merger in the case when the tertiary is a supermassive black hole. Okay, right? So here I'm imagining you have a nuclear star cluster and you have a binary here which you want to merge, and you have a supermassive black hole, right? In this case, of course, if you want this binary to be stable, dynamically stable, you better have A out much greater than A. So by definition, the octopole is always small. If you don't have that octopole effect, it's just a very simple, clean, analytic Bidov-Kozai effect at work, right? Except in this case, because you have supermassive black hole, you have a spin. This guy's spin is actually very big. It's actually could be bigger than the orbit, right? Could be comparable or bigger than the orbit, L out. So therefore, there are several relativistic effects one can study, right? That can actually affect the dynamics, right? And this problem, we have a three-body problem, including all kinds of GR effect. It's if you are a real relativist want to study this problem, it's actually very interesting. You find it all kinds of extension, right? Right? If you want to do this rigorously, it's actually not trivial. You can do this. It turns out you can get all the equation easily if you make an analogy. For example, right? This guy. If you treat this guy as a spin in top, this is basically the binary problem. This is the orbit. You can easily imagine this is a spin. Then basically it's a binary problem. This has been studied before. So there are several of this GR effect one can study and incorporate into the secular dynamics of Kozai oscillation. Okay, and so let me just show you the result, right? So here is the standard Kozai, as I said, right? It's a periodic, everything analytic, quadrupole Kozai, right? Eccentricity oscillation is regular, but now if you include some GR effect, I talked about all kinds of precessions, right? So here, Chris, here is not, this is not very far. This is actually 500 AU. Let's give you an example, right? You can see this thing become more chaotic, right? And the main takeaway for this thing is that this GR effect associated with the spin of the black hole can also broaden the Kozai window, Kozai window. Can also broaden the window. Namely, if you don't have this additional GR effect, you can merge only within a narrow range, 90 degrees. But if you add this GR effect, you can have a broader range of angles. So increase the chance of merging. Why is that?
Yeah,
Why is that? Well, the reason for this is actually quite simple. So let me just give you one example. So here is the, let's talk about, right, you have a spin, you have an L out, right? So of course the spin will make because it's a spin, there's a spin orbit coupling, S3 of the supermassive black hole is coupled with the orbit, right? So the result is that this L out is actually not fixed. It's changing, but these two vectors are orbiting around each other. So in the usual Kozai problem, L out is fixed, right? And you have this Kozai. But here, this L out is actually wobbling. It's wobbling. So, so that's what I'm talking about here. This precession frequency of L out relative to S3. The frequency associated with this thing. It turns out that if you have, on the other hand, this is the binary we care about, right? So this guy, of course, L in, is also precessing around L out because you have this Newtonian precession, right? And this is essentially the Kozai, lead-off Kozai effect, right? So if these two time scales are comparable, you can imagine there's some incarnation resonance, right? Incarnation resonance. So even when they initiate this L in and L out, it's relatively small angle because of the resonance. These two angles, L in and L out, can become large due to this incarnation resonance. Okay, and then that can bring the system into the lead-off Kozai regime. Okay, so that's the way to understand it. Okay, so this GR effect basically increase the merger window.
For these numerical results, what's the ratio of the binary size to the Hill radius of the binary?
The binary is certainly dynamically stable. It's inside Hill radius.
But is it far inside, or is it just a little bit inside? Or?
Let's see. You can do the thing, right? So it's
okay.
No, it's 0.1% of the can look at the number. Okay. Also, maybe 10%, 1%, few percent.
Yeah, something like that.
Okay.
I'm kind of surprised this spin is the the spin effect's so strong. What about neighboring stars in the same orbits? Wouldn't they be much more important?
Absolutely good point. That's indeed. If I'm talking about yes, indeed there are. If you're imagining these binaries in it's part of the star cluster, you have to worry about the cluster environment that can also affect the Kozai oscillation, even when the supermassive black hole may still be dominant. So here we're talking about something very close, relatively close.
But still, spin is such a weak term.
Well, it's all this two ratio, I think, right? It's all this ratio. It's true, this guy is, but this other thing is also small.
Higher than the GR precession.
It's all this ratio. You have to look at this ratio, these two frequencies.
It just happened.
Okay. Okay, so now let me talk about spin orbit angle. Remember this angle, the angle between the spin of the individual black hole and the orbit, right? That's can be measured or constrained, chi-effective, right? And so that's what is the spin, right? What is the spin or orientation of this merging black hole, right? So the question is, this tertiary is changing the orbital orientation of the inner binary, right? So this orbit goes through all kinds of dynamical process. During all this time, what's happening to the stellar spin? That's the question, right? What's happening to the black hole spin, right? And of course, it's not going to sit there constant, it's fixed, it's actually changing because I already mentioned, right? When you have a binary, the spin is actually precessing around L. This L axis binary, that spin orbit coupling, post-Newtonian effect, right? Or called the CITA precession, right? So S of the black hole is certainly precessing around L of the binary, of the inner binary. On the other hand, of course, this L of the inner binary also changing during the Kozai process, right? It's undergo precession, it's undergo mutation, it's wobbling basically, right? Has certain frequency. So the spin dynamics depend on the ratio, depend on these two things, right? So this L out is the outer binary axis, right? So L is undergoing precession, right, nutation due to Kozai effect, and the S is trying to move around it, right? Right. So you have to compare these time scales, right? And this time scales, this ratio of frequencies actually change as the orbit undergo decays, because if you look at the expression, initially the orbit is very big, the inner orbit is very big, so this ratio is much less than 1, and then eventually the two little black holes become very close to each other, and then of course the spin precession will be much higher, much larger. So, and there is transition, right? During the transition, there's all kinds of things can happen, right? Some resonance can happen, and okay. So here is just an example. Just an example, right? So same example as before. Same example as before, right? I have 30 plus 20 inner binary being perturbed by 30 solar mass tertiary far away, right? Right? Initially it's 100 AU, but eventually merged. And here, the only thing new here is this angle between S and L, the spin of the black hole and L of the inner orbit. So initially it's 0, right? And then it undergoes, this is log time, so that's why it's squeezed here, right? And it undergoes all kinds of things. And eventually you can see in this example, they undergo crazy oscillation and eventually settle down into a value which is close to 90 degrees. Okay, in this example. Okay, and you can do a population-wise, try to look at all kinds of parameters, right? And here it's basically plotting, for example, plotting the final spin orbit angle as a function of the initial inclination of the orbit of the tertiary, right? Right, and you can actually see there is a kind of clustering around 90 degrees, right? Clustering around 90 degrees. So there is actually a 90-degree attractor, which can be understood using the concept of adiabatic invariance. Roughly speaking, the following thing, it's not exact analogy. Basically, if you imagine you have a axis here, it's changing slowly. This guy here is try to move around it. If this guy moves slowly, the angle is being conserved. Basically, that's the adiabatic invariance, right? Right. So this guy moving around with 30 degrees. If he's moving, it's going to be always 30 degrees, right? So this is can be the problem can be cast into that problem, basically.
And these are the evolution here is being calculated using secular equations.
This is all secular equation, yes. This is all secular equation, coupled with spin. Okay, so there is depending on, you can imagine the binary, there are all kinds of parameters. So depending on the parameters of the triple systems, you can get a broad distribution of the final spin orbit angle. There's a slight peak around 90 degrees. That's that 90-degree peak is due to that attractor. Okay, now is this consistent with with observation? And right, and here is the current O3 data for chi-effective constraint. Okay, right. It's you can, I think, I was just talking to Maya. You can see people can do more sophisticated things. It's mostly zero, a lot of zeros, and there are certainly a few positive things, right? And so it's interesting. Okay, so this maybe there's some. Okay, this can be constrained. Okay.
For your calculation, though, what do you assume for the? This doesn't tell about how fast the black hole is spinning.
No, does not. Yeah,
So
this effect does not depend on magnitude of spin, because the spin-orbit coupling does not depend on magnitude. Does not depend on.
yours, but
They depend, exactly. Yeah. That's a very important point. This mechanism, this predict does not depend on the magnitude of the spin at all. Fundamentally, it's because the CITA precession, right? The precession rate does not depend on the magnitude of spin. It's very different from Newtonian. If you have Newtonian, rotating body, that precession rate actually depends on magnitude of spin. In this case, does not depend. So it's actually different. Okay. Spin orbit angle. And then finally, just quickly, given the way this merger is induced, right, because this orbit becomes very eccentric, inner orbit, very, very eccentric, 0.999 sometimes. So even though you have still a lot of decay, you can still retain some eccentricity when the binary enter the LIGO band. So, and this is very approximate, sort of a lot of uncertainties depending on the population, right? And typically you find out there are some of them will have non-negligible eccentricity on 1, on 2. Okay. So that's the sort of the summary of this, right? There may be modest eccentricity, there's a broad spin orbit angle, and this everything being equal, the unequal mass merger is more likely. That probably ruled out this galactic tertiary induced merger that have been studied by many people, including us, right? And in the nuclear star cluster, you have this GR effect that can affect the merger window, right? Again, everything being equal, if you have a supermassive black hole with a high spin, that tend to broaden the window more, okay, more likely. All right, so that's the second classes of merger channel, tertiary induced merger. Now let me move on to the black hole merger in AGN disks. So this is so the idea here is that has been around for a while, right? Basically, you have supermassive black hole, you have AGN disk. It's known that AGN disks are gravitationally unstable at some distance, typically a few AU, right? And they can fragment into stars, massive stars, and therefore form black holes, individual stellar mass black holes in AGN disks. Moreover, you could have nuclear star clusters, of course, around this supermassive black hole, and some of them will be captured. Some of the stars will be captured by the AGN disk, and therefore, again, becoming individual black holes, right? And so therefore, you could have a possibility of black hole mergers inside the AGN disks, right? So there are a lot of physical processes that are still being studied, right? The capture, how the star get captured, and binary, once you have a star here, and how they migrate, and how do you form a binary, stellar mass binary in the first place, and so on, right? Roughly speaking, one can divide this merger channel into two, classified into two ways, right? The first one, it's I call them gas-free, or essentially gas-free merger. So you can imagine two black holes, stellar mass black hole, that have been brought onto a plane by the gas, by dissipated processes, and then they can, once they are confined in the plane, they have more chance to find each other and they merge, right? It's sort of, so AGN disk, the gas disk play an indirect role. You bring them into a plane and then they can imagine each other.
But does it bring them into the plane?
That is,
Because, for example, if it's gravitationally unstable, it'll have all these density waves and so on, and the mass.
Maybe not, yeah.
The mass of the spiral wave can be much larger than the mass of the star. It kicks it out.
It's possible. It's all possible. Yes. Yes.
Yeah.
Yes. I'm just yes. That's all possible. I think this kind of thing. Yeah. But generally speaking, if you think about something, kind of the damping effect. Right? The gas is sufficiently massive, it dampens the thing into the grinding down the orbit. Right? But okay, maybe not in the perfect plane. And the second is gas-assisted merger. Right? The merger really got helped by the gas dynamical processes. Okay, so let me talk about these two different, give some examples of these two different ways of merger. Okay, so let me do this problem. First, talk about this problem. So imagine you have this example of gas-free merger in the disk. Okay, so let's think about the following problem. You have a supermassive black hole. You have two little black holes, right? Orbit A1, A2. Initially, they are both in circular orbits. They are in a closely packed, nearly circular, nearly coplanar orbit around the supermassive black hole. So you may imagine they can be brought, this kind of configuration is brought together by the migration, right? In the AGN disk, you have they migrate and there's a migration trap, or they catch up with each other, and then of course, right, and the gas does not last very long, they just gone, and right, or the gas is sufficiently small, does not play some important role. Okay, so that's the configuration we're dealing with. Now, of course, it's well known that if the A2 minus A1, if the two orbits are very close to each other, how close? If they're closer than roughly this value, 3.5 RH, the Hill radius, the mutual Hill radius of the system of two little black holes. So the Hill radius is basically the radius within which, if the two little black holes are separated within that Hill radius, the mutual gravity is greater than the tidal gravity from the supermassive black hole. Okay, for the Hill radius, right? So it's well known that you can actually show this thing. It's well known from planetary dynamics. If this separation is less than this value, then these orbits are dynamically unstable. Okay. So then the question is, what's going to happen to the little black holes? Right. So that's a well-defined question. Okay. Now, this is really similar to planetary dynamics problem, right? In the planetary context, if you talk about two giant planets, orbiting around a star, right? And you do the same problem. Many of you have done this kind of problems, right? And there are usually three outcomes, right? The first is that the lower mass planet will be ejected, right? The second outcome is that these two planets may collide with each other. The third one is that one of the planet will be injected into the star, collide with the star, right? So these are the three possible outcomes in the planetary situation. Now here, it's essentially same problem essentially, but we have two little black holes orbiting around the supermassive black hole. It's a bit different. The only difference is that the mass ratio is much more extreme, right? It's much more extreme. In this case, you can easily convince yourself that the first two, ejection and injection are not possible. It will take many orbits. Are not possible simply because look, you have this big guy, supermassive black hole, moving around, and this injection or injection are all due to mutual interaction, right? The mutual interaction is not strong enough, basically, compared to the this big guy, supermassive black hole sitting there. So it's not possible to eject or inject, are not possible. So the result then is that you have these two little black holes undergo erratic motion, chaotic motion, moving in that region, not a regular orbit, and they will move around forever, more or less, right? And occasionally they are going to experience close encounters, and their separation will be close to Hill radius, right? So that's what's going to happen. That's basically what's going to happen, except once in a great while, these two little black holes will be very close to each other, can become very close to each other. Then when they're very close to each other, the relative motion between the two little black holes can radiate gravitational wave. When two things coming close to each other, the relative motion is sufficiently fast, they can radiate gravitational wave. And if you are sufficiently close, the energy that's radiated is sufficiently large that can immediately make the two things bound to each other. Right? So the typical energy scale here is G m1, m2 to you have a Hill radius. Right? So if you can radiate sufficiently large, that depends on the separation between the little black holes, then you can bound, right? And in one shot, the binary is formed, right? And if you do that little calculation, you find that the relative separation is very small, -4, small. Remember, the typical separation is Hill radius, right? But here you very close encounter means they come very close to each other, 10⁻⁴ less, right? And so this is the capture radius for forming a permanent binary due to gravitational wave Bremsstrahlung. It's like an electromagnetic Bremsstrahlung radiation, right? It's that gravitational radiation. So you can ask how likely this is going to happen, how likely this can happen, or how often it can happen. And this actually, it's like a lost cone problem that many people may be familiar with, right? You have, stars in the galactic nuclei. All the stars scatter each other. Once in a while, a star will be kicked into a low angular momentum orbit, get sucked by the supermassive black hole. Here, in a way, it's similar, right? You have this two little black holes moving around a big black hole. They're moving around each other, but once in a while, they may be kicked into an orbit such that the relative angular momentum is so small, they basically collide with each other, right? So this is it's a kind of relative loss cone problem. And you can of course do simulation, try to do this, that take a long time, try to see how often this can happen. But you can also try to do the scaling, try to think about how that happens, and you can derive that probability. And that probability, it's basically roughly ratio, so it's like 10⁻⁴. If our the separation between the two little black holes, the capture radius is 10⁻⁴, then you get a very small probability, right?
Does that assume the two binaries, the two record space coplanar exactly?
Yes, this can be easily derived. This can be derived. Yes, if you have a perfect coplanar thing, the scaling is different. This is actually assuming a 3-dimensional.
I was expecting something.
Okay, we can do this. Just distract a little bit. But, okay, if you have a perfect coplanar, then the scaling is different. Okay? This is actually the point. Is if you have a small mutual inclination, the scattering process will pump up the eccentricity mutual inclination to the value actually comparable to this. So it's actually this is actually relevant.
How likely is it that you get into one of these orbits like the moons of Saturn that just switch around? But there's these two moons of Saturn, which just one is on the outside and then one catches up and it becomes the outside one, the other one becomes the inside one.
Oh, then we have, yeah, you mean the co-orbital thing? Co-orbital?
Yeah, but not quite co-orbital, right? They're just stopping. Huh?
Just don't capture.
Right, but I mean, if the likelihood is small, then maybe that is equally unlikely. And that's the first big one.
Anyway, this can happen. If you once you have this, you can actually compute the rates. If you tell me that the flux of lots of black holes coming into this kind of orbit, you can actually calculate the rates. And now, so carrying on with the story. So basically, you have this one-shot capture, right? At capture, the orbital frequency at the pericenter is actually, if you use typical numbers, right? The 8 solar mass supermassive black hole, 100 solar mass, stellar mass black hole, typical location in the AGN disk.
Why is that a typical location?
Well, this is not exactly. This is just in some of the literature, people are talking about the migration trap. People build models, right? Not so sensitive, right? If you larger, right? Okay, and you get something that 1 Hertz, which is happen to be between the LISA and the LIGO, right? So it's not quite LIGO yet. But however, this orbit, of course, captured highly eccentric orbit, and it basically you can easily figure out it will take only a few orbits, will actually merge, will enter the LIGO band. So when it enters the LIGO band, it will automatically have large eccentricity, okay, by construction almost, because it's a highly eccentric orbit. By construction will always have large eccentricity. So this mechanism always produces eccentric mergers, okay, 0.1 or larger. Okay, and this mechanism also produce broad angles. So what do I mean by that? Right, basically, these two little, remember here is the supermassive black hole. This two little black hole initially is more or less coplanar, right? But not complete coplanar. It's different. They may have a very small angle, right? But when they come very, very close to each other, 10⁻⁴, here it is. It's essentially 3-dimensional, right? So actually, you can easily convince yourself that this is borne out by the simulation. Look at the blue curve, right? It's basically a isotropic spin orbit orientation. Basically, the orientation of the little binary relative to the original AGN disk is isotropic. Okay, so now of course, if you assign a spin for individual black hole, then you may also get a broader spin orbit inclination. Okay, So that's the, so this is a sort of the example of the merger in the AGN disk in the plane, quasi-plane, but not the gas does not play a direct role, right? Now, finally, let me talk about, 5 minutes, the gas effect. The gas effect, right? So let's do the same problem, right? Initially, you have a supermassive black hole, you have 2 little black holes, right? And separated by, let's say, a few kiloradius, 2 kiloradius, right? And so this is a hydrodynamical simulation by Jialu using the computer, Los Alamos computer. Hui Li has a lot of computer time using this thing. Right, let's see what's going to happen, right, basically. And this is using the simplest physical ingredient, isothermal equation of state, viscous, putting viscosity by hand, that kind of thing, okay? And so each little black hole has its own mini disk, all resolved, right? And then they come together, and they catch up with each other, and then they merge. In this case, they merge in the form of binary. Of course, we put in sufficient large gas density. You have to have sufficient large gas density.
What's the mass of the mini disks compared with the mass of the small black holes?
Oh, I don't have the number with me. Smaller, mini disks, but it's certainly smaller. I don't have the number. Yes. Okay, the mechanism of this is basically you look at this orbital energy. Here's a separation between the 2 little black holes, right? So they come from far away from each other, and then they come closer. Not much energy dissipation, and then dissipation. So we call this departure drag. Basically, what's happening is that basically it's two mini disks coming in. They dump a lot of gas in that region, and then when they try to come out, you have a lot of gas drag. Okay, and this outcome of this obviously depends on the gas density, right? It also depends on this separation, this K parameter. This parameter, A2 minus A1, and K is the separation in units of kiloradius. And it also depends a bit on the phase. Okay, so it's not it's a probabilistic event. And so this kind of hydro simulation is actually very expensive. So it's actually useful to do some toy model. So I try to do some toy model calculation, try to get some insight. Okay, so here it's not hydro calculation, but a simple toy model calculation. So what we do here is basically imagine, again, you have these 2, supermassive black hole, 2 little black hole, right? And this, of course, all the gravity is in there. But in addition, you just add a drag force on each little black hole. The drag force is proportional to v, velocity of the little black hole, minus v Kepler. So imagine you have a global Keplerian disk, right? So there is this drag force. Now, you should not believe this. Of course, this is too simple compared to the real thing, but nevertheless, it's actually quite interesting. In fact, people use this kind of thing, this kind of model for studying KBO binary formation some years ago. Okay, and okay, so here is the result. Okay, so here is the vertical axis. It's the drag coefficient 1 over tau, and horizontal axis is that K parameter, the separation, right? And each dot represents a calculation, basically, right? Black dot, black region means you don't form binary. Red means you form a retrograde binary. Retrograde means the binary orbital axis is opposite to the original AGN disk. And blue is the prograde. So it actually has a rich structure, and okay, it has a rich, very rich structure. Now, it's because the trajectory can be very complicated. Let me just let me putting this on yesterday, but so why you get this kind of things? Okay, for people who haven't studied this, become very strange. So let me explain this a little bit. Okay, so what happens here is this: right? So here's the supermassive black hole, right? So I'm the little black hole I'm moving, and this is this little one, and this is moving slower, right? So I'm catching up with that guy, basically, right? So obviously, right? So this guy moving slow, I'm catching up, right? So obviously, if K is large, there will be no deflection. Basically, they will not be, they're basically not going to capture, of course, right? If it's too small, if this guy is, I'm here, I'm moving, and this guy is too close, K is small, then it's also not going to capture. Why? It's because, look, I'm catching up with the guy, this guy here, I'm here, right? I'm exerting a force, gravitational force on that guy. I'm slowing him down, pulling that guy down, right? I'm depleting that guy angular momentum, giving basically drain the angular momentum from that. I'm catching up, right? During that process, I'm slowing him down. So basically taking away angular momentum from the one outside. So the outside one is losing angular momentum. If you're losing angular momentum, it will go to smaller orbit. So what happens is that for orbit that is sufficiently small K, it's going to go into the horseshoe orbit. It's going to basically join, but basically it's not going to be captured also. In between, you can get a very complicated trajectory. So, okay, right? So small K and large K, nothing happened, cannot capture. In between, you can get all kinds of complications, right? And that's what this kind of thing. So you can sometimes, depending on K value, you can get all kinds of trajectories. Okay. And this is this kind of trajectory. It's it's studied by a famous paper by Petit and Penon in the 80s. Okay.
So just always as temporary capture.
This is all captured. These are all real capture.
I know, but it's because they end up in some
temporary things. You can these are captured thing, and these stripes correspond to the comeback second time. This is the first time. Okay, and okay, and here is actually back to the real simulation. So even though it's expensive, Jialu has actually gradually completing the survey of all the parameters. So here it's it's a real thing, right? Hydrogen K, and here is the drag coefficient, right? The drag coefficient, of course, it's basically corresponding to the density. It's a parameterization of the density of the gas. Okay. So you can see again, if it's larger, nothing happened, cannot capture. Too small, nothing capture, but you can get this retrograde, prograde, and corresponding all kinds of trajectories. Okay. All right.
But you're assuming that K remains constant during the interaction.
No, this is the initial K. This is the initial K. Just they're coming in with some K, initial K. Now, this is the, basically the initial.
Sorry, no. I mean, you're assuming that tau remains constant, right?
No, this tau, okay, no, this is actually not a real, this is just the sugar density. It's just a parameterization of density.
This is a real simulation.
This is a real hydro simulation. So I'm basically, this vertical axis is proportional to gas density, F1 density, right? This tau is basically, I imagine the type 1 migration eccentricity damping in that, the formula connecting tau to that density. It's a way of parameterizing. And I guess the take one message here is that in order for this thing to work, that's something we did not appreciate before. You really need a high density such that you can have actually very existing orbital period. Okay, so you really need a very people doing planets. This is actually very strong damping, very strong friction time scale.
You need a lot of gas.
Need a lot of gas. So this may or may not, right? And
Well, that's because you're counting 100% capture. If you say I can have smaller capture efficiency.
what do you mean small cap?
But some of this chaotic orbit doesn't have to get captured, they can get out.
Yeah, so this black thing don't capture. They just they come in trap and then become they separated, become stable, separated.
The red ones are the ones that enter into temporary capture, right?
Oh, eventually captured. So coming in, this is the heel radius. This is fully captured. It's fully captured. They become
But the reason they become captured is because they enter into chaotic orbits.
they enter the chaotic orbit, yes.
And therefore, Yeah.
See, this is relative orbit trajectory. So this case, we just leave and then never come back, basically.
Yeah.
They have to spend time inside the hill radius.
They spend some time, this is the hill radius, they spend some
Oh,
time.
that's not enough.
Not enough, yeah,
You
not
want the
enough.
one that spends longer time, and that's those are the capture ones.
Yes.
You don't have to 100% capture. You can capture after a few, synodic time, sure.
Sure, there are some probability. That's right. We're basically trying to map out this parameter regime condition for capture, basically. And, okay.
So I was going to ask, how do you get them, if you're appealing to migration, to get them to these really close K values? What's to stop them?
Okay, so this is we're not the other calculation is much more complicated to do. We like to do a calculation where you start two little black holes far away from each other, let them migrate, and then that one we have not done. That one is very time. We don't know how to do it.
Planet people would say they just capture in resonance and never get this close, but maybe you're saying the Ks are.
Oh, well, okay. In this case, we are not going to capture into resonance. The reason for this is that if you take typical parameters, the migration is too fast compared to mutual interaction. The time scale, if you compare the migration time scale and the libration time, the ratio is
So
they don't capture in mean motion resonance. Okay. They come in and then they okay. So
because the gas density is so high.
it's just the time scale is very long. You need many orbits. And you also need to resolve individual, because to calculate this kind of thing, you need to resolve the individual mini disk. For us.
You're talking about the mini disks.
Yeah, because the whole capture process involves the collision of the mini disk. So you actually need to resolve this thing. That's why it's making it a bit expensive.
Oh yeah, no,
That is
expensive, sure, but
That's what's
I'm
happening.
saying in an actual AGN disk, right? Presumably before they got this close, they started out on much further separation.
Exactly. Yeah,
So-
we have not done that problem. We'd like to do it, but for the toy problem, we can do it. We are doing it. But for this real hydrogen problem, it's so hard.
So you're putting energy into the gas, internal energy into the gas, because,
What do you mean? Like,
well, the gas is obviously must be heating up in response to absorbing relative motion of the
we are using we're using isothermal equation of state.
That's what I was worrying about.
So far, the isothermal equation of state.
That's what I was worrying about.
Okay.
Wouldn't you just blow away the gas, a lot of the gas?
Uh,
If you didn't let the gas radiate away, if in fact if it was,
isothermal means radiate very efficient.
I know, but suppose it was adiabatic.
Yeah.
Would this work?
Then I don't know. We don't. I think.
Create puffy halos that would become more diluted and reduce the drag.
Maybe we have not done this. We have done. Okay, let me. Anyway, so this is sort of formation, binary formation. So binary formation. Okay, let me just last 2 minutes finish the thing, right? So finally, this will come. State issue. What happens when you have a binary already formed, embedded in the AGN disk, right? What's the effect of gas on this binary? How does the binary, form? What is does the gas help make the thing shrink? Suppose this orbit is still sufficiently large that gravitational radiation is still not efficient. You need the gas to help. Like, what's the effect? And this is a problem that has been studied by many people in recent years. Okay, and so we have been doing this thing, doing this sharing box calculation in 2D. People are now doing 3Ds now, but it's 2D problem. Go to the rotating frame, you can do the sharing box calculation. Now there are several. It looks like there are a lot of several length scales and velocity scale. It turns out there are only really two time scale, two dimensions ratios. One is this ratio of the Hill radius divided by the orbital separation. That certainly should be greater than 1. Another one is this. It's basically the ratio of any of this length scale ratio related to this mass ratio and the thickness of the disk, which is related to the equation of state. And for people doing planets, it's like the mass divided by thermal mass. Thermal mass. Exactly. And of course, depends also on the eccentricity, the mass ratio of the individual binary, and 1 and 2, that kind of equation of state, right? And so we've done some of these problems. You can see the flow structure is very rich, very complicated. You have, pair of bow shocks, spiral shocks colliding with each other. and then we actually have try to resolve the individual black hole and think particle, and try to calculate the accretion rate and also the orbital evolution. Calculate the force of torque on the binary for the gas. Okay, and so here is not to just show some of the results. For example, here is the final A dot over A is the orbital decay rate, and this is for some systems, right? Some parameters, and this is alpha parameter for the viscosity. You can see it's shrinking the orbit negative, but sometimes it's positive. If you have, you're right, Chris. This equational state make a big difference. This is gamma equational state. This is gamma. This is isothermal. They make a big difference in this problem. The size of the absorbing sphere also matters, right? So, okay, so so the problem, it turns out that this is actually a complicated problem. So if you ask me whether the orbit will decay or expand, we put a binary in the AGN disk. The answer is actually not so clear. It turns out that the answer depends on the gas thermodynamics, depends on viscosity, depends on how each black hole accrete. And well, that's just life, quite complicated, right? It's reminiscent of the problem of circumbinary accretion. If you ask, you have a binary and you have a circumbinary disk, whether whether the binary shrink or expand. It turns out that a lot of those factors also matters. Okay? Retrograde binary. If you have a binary retrograde, I told you that you form retrograde binary. That always decay. That's actually pretty clear. Okay. Okay. In general, the orbital evolution of the binary is much faster. So the binary can shrink faster than the migration or the central mass in the AGN disk. Okay. So that's this sort of gas-assisted merger. And finally, just a note that of course, when you have black hole merging in AGN disks, there's a possibility of generating electromagnetic counterpart. And there have some claims, in the last few years, right? Some VTF event coincide with this black hole merger event. And last year there was this claim VTF flares, and they claim it's pretty unusual. So they claim maybe it's a merger in that AGN disk. But we really don't know. Right? Whether this is observable. It's not clear. So this merger happening in the disk. The disk itself is so bright. It's not clear. Okay, so that's all I want to talk today. So let me just summarize the lots of work remains to be done in the coming years with a lot of data, more data, especially on black hole mergers, right? And it's probably the standard isolate binary evolution. It's a default, probably will work, but we don't know yet. Okay, it's right. They have some generic predictions. And there are several different flavors of dynamical mergers that can play some role, and some of them can be constrained or ruled out, perhaps more definitively in the coming years by data. So that would be nice. Thank you.
A little bit of answer questions already. I'll give people a chance to take out. Otherwise, questions.
Were Jarvis simulations 2D or 3D?
Which one?
Jarvis?
It's all 2D. It's 2D.
So
the 2D, yes.
with the difference you found in the gas-free mergers between 2D and 3D, is there some extrapolation you can make to 3D simulations?
Well, it turns out for this problem, look, if you look, one of the things, all this time scale, this essentially corresponds to eccentricity damping rate. With this kind of damping rate, they actually damp very quickly to zero. But if you want this to work, so
Okay.
so
Okay.
we have not done 3D. That's an honest answer. So this is mainly because it's very expensive. So yes.
But so if you want to damp the relative motion of two black holes, you need a lot of gas.
Yes. That this actually corresponds to gas.
Okay, so the gas, in order not to be gravitationally unstable, has to be geometrically thick.
Right.
And if it's geometrically thick, it has a large cross-section to absorbing energy from the central black holes when some gas accretes. So what I'm worried about is, if your disks are substantial in size, I don't know how many gravitational radii you're talking about, I would think it has to be like thousands or more.
Right.
Then a small amount of radiation from the center could blow out the gas. Because you're not resupplying the gas during this interaction. You're not resupplying the gas, right, by continued accretion from some larger reservoir.
Yes.
You have a finite amount of gas in your certain black hole disk. And it's also absorbing a lot of kinetic energy. It sounds to me like in practice it might be a fragile thing, that it would tend to just disappear.
The gas will be gone.
Yeah.
But this stuff needs a lot of gas. This is a huge. This
Right.
actually corresponds to a lot of. I'm not sure you can. This.
Okay. And in
I
some
have another
cases,
plot. I didn't have it. Okay.
in some cases, this is not isothermal. This is
This one is isothermal.
This is
Sorry, I
isothermal.
talked about two things. Sorry.
Yeah.
This is a capture. This calculation is starting out with two little black holes orbiting big one.
And so the
Trying to
gas,
capture. That's a difficult
the
calculation.
gas is able to radiate infinitely fast any internal heat that's been added to it by the dissipative interaction.
And the black holes have no accretion limits.
And black holes have no accretion.
This. Okay, hold on. Okay.
Yeah.
This one. Black hole doesn't have accretion. Does not have accretion. Does not. It's just treated as gravity. Just like what people do planets.
Right.
Gravitating body that had a mini disk. No accretion. This one has this calculation. So this calculation has no. This particular plot basically is just a black hole is just a gravitating source with some softened length. And then everything is isothermal. But it's important to resolve this small region basically. So that's what it is. So.
Fun calculation.
Okay. But the other problem I did, I talked about it. This one is different. This one is you already have a binary already formed, and try to understand how whether they evolve. So both of these problems, these have been done a lot.
How come you're not working on global crystals?
Oh, because it's already done. I don't know how many people have done.
What do you think? Is it relative?
I don't know. I just the physics is very clean. I mentioned these uncertainties, like environmental uncertainty. I feel I'm inadequate to control. I cannot control the environmental uncertainty.
So you don't know which one's more important around this?
I don't know. I don't know. What we can talk about it.
I don't know. I wonder if you do.
I don't know.
Well, the main thing that really has not got enough attention in the AGN text, in this context, is the dynamical heating of the black holes.
Dynamical heating of the black hole
holes.
on the disk,
Yes.
on the AGN disk.
Yes. So yes, if they were in very eccentric inclined orbits, they will feel drag, right?
Yeah.
But do they really become dynamically cold enough to form binaries, or do they maintain some intermediate distribution of eccentricities and inclinations?
Oh, what is the same?
Because the
Yes.
disk is dynamically active.
Yes, this one I think.
And people just ignore this.
Well, this is the the kind of calculation I think we're beginning to do. This is a little idealized, of course. Laminar,
But we're in a position to actually have the background disk be gravitationally active to see what it does, right?
Well, this is sufficiently close to the supermassive black hole. It's actually gravitationally stable. It's not a passive. It's not far away. Not too far away. This is like 100 arcs, few hundred arcs. That's what the kind of thing people are talking about. Okay.
Thanks again. Anybody else? Should have talked to you. Oh, there's a. How strong is the?
How strong
How strong is the gravitational Bremsstrahlung?
it depends on gravitation depends on the separation. There's two things coming in. The strength of gravitational Bremsstrahlung depends on how close they are, basically, right? And if you know the separation, you can compute. Okay. All right, thank you.
So Don,
Thank you. Thanks.
It's not Edinburgh. No, someone else.
Okay.
So Don, you were delayed by the snow.